Hello everyone, welcome to Multivariate Statistics and Machine Learning. In this video I will be talking about variable selection and about cross-validation. If you would like to study this yourself, then look at section 4.6 variable selection and cross-validation in the lecture notes. So if you recall, in the last video we were talking about variable ranking, or feature ranking. So we have variables, let's say we have predictors x1 to xd, and we showed that we can, for instance in DDA, the influence on outcome y is measured by a t-score, ti. So we can actually rank the features by, for instance, ti squared, or by the absolute value of the ti, and that would give us a list where the most influential features are ranked first and the least influential features are on the bottom of this list. So we have a ranking. So basically top, middle, bottom, and this has, at the top we have large values of ti, and then here we have low values of ti, and then we have something in between. So that's our twilight, so they're neither large nor low. So these groups correspond to three interesting groups, namely, so this is 1, 2, and 3. So 1 are the features where we are sure, or variables features, where features that clearly contribute to predicting the outcome, clearly are important for prediction. Then in 3 we have features that are clearly not important, are not relevant, and then in 2 we don't know. So these are the 3 groups, and what we have to, our problem is now to find a threshold that allows us to keep the important features in the predictor. So we'd like to find, so for prediction, we would like to remove all the features that are clearly not relevant. All xi that are clearly not relevant. So in other words, we'd like to remove features in group 3. So this is what we, and this is a different approach than compared to if we would like to find the features that clearly are important, because then we would just retain the features in one. But in practice, for prediction, we can only remove features that we are actually sure that don't contribute. So we have to keep features in 1 and 2 and remove features from group 3. Keep 1, 2 and remove group 3. So the question is, how do we do this? So and a useful way to do this has been discussed in the last term, and I'll briefly review it here. So a good way to do this is use false discovery rates, and there are several ways to do this, so I'll just describe one way. And so what we do normally in false discovery rates, we have test statistics. So these would be our z-scores or t-scores. So we have z-scores 1, zd, then we model them using a mixture distribution, fz, and that's a two-component mixture, namely a null model plus an alternative model. So the key thing is that this is our null model. So this usually also has a parameter, and typically it has a some, let's say, variance parameter. And this is the alternative model. And this has, typically it's actually non-parametrically modeled, so it's non-parametric. And this is typically from a parametric family. So now, once this is fitted, we can compute the probability of a sample being in the null group given Z. And this is called the local false discovery rate. So local FDR, and it's simply defined as follows. So we have the mixture density, and then we have the null the null part of the mixture, and of course we have a fitted model, so everything here is estimated. So this is our local FDR, and this gives us exactly what we want. So we can compute for each feature the probability to be in the null group. So we can use, so this is also written as well as FDR ZI. So we can use this local FDR to identify the null features and then remove them. So for instance, we could say remove all ZI for which FDR of ZI is, say, larger than 0.8. So if the probability to be in the null group is more than 80%, we are happy to let them go. So you can also use this method to actually find features that are actually contributing. So this is our group. How did we call it? It was group 3. So this is our group 3. We can also use this method to find features in group 1. So features in group 1 would be all Zi for which the local FDR, let's say, is smaller than 20%. So these are just some arbitrary thresholds, of course, but if we impose that the false recovery rate should be smaller than a certain value, then we can be reasonably sure that it's actually the alternative distribution. Of course, and it's easy to see that for the false discovery rate, so the false discovery rate, there's something also called the false non-discovery rate, and that would be just 1 minus. So that's why these things I wrote 0.8 and 0.2. So this is basically giving us group 1, and everything in between is of course in group 2. Okay, so that's one way how to do it. So you have your Z-scores or T-scores, and then you compute false discovery rates. The second way to do it, or an alternative way to evaluate would be, is actually more direct. Evaluate the prediction accuracy or prediction error. So estimate the prediction error of a model, and then we would compute this for several models and then compare the prediction accuracy of several models. And to do this, we need something that we haven't discussed so far, namely we need validation data. So there are 3 types of data. Two of them we already encountered. So we have training data. So this would be X and Y, and we use it to learn the predictor. So far so good. Then we know that we have test data X and Y is unknown, and we would like to predict Y. And then finally we have validation data, and this is also X and Y, both known, but not used in training. So this is basically a bit of a luxury to have validation data, because normally you would of course try to use all the data you have to learn the predictor. So, but for the moment we have, let's assume we have validation data. So using validation data, we can estimate the prediction error and we do this as follows. So we because we need two things. We need to have the true label, and then we need to have an estimated label for the same data point. And that comes from, if f is our prediction rule or trained prediction rule, this would be f of x, and both y and x are from the validation data set. And then we can define an error function that takes these things as input, and depending on our model we can define this as follows. For example, we can say we would like to have the squared error, so y hat minus y, so that's the squared error, or I can say loss actually. So, or we can have 0, 1 error, it would be 1 if y hat actually gets the prediction right, and 0 otherwise, and so on. And there are lots and lots of possibilities, and in fact this is somewhat linked to two things, to the model itself, and also there's a theory or framework called scoring rules that provides a nice framework for this prediction, so you can have a probabilistic measure as well, and then that links loss functions with distributions and other things, but we're not going into details now. So this would be the prediction error. The definition: once we've set up a prediction error, we can compute the mean prediction error, which is basically the expectation of this thing. And this can be, in turn, this is estimated, so let's call it PE, and this is estimated by the empirical mean prediction error. So this would simply be 1 over m, and then we take the average over the outcomes of this error measure for all the data points in the validation set. So m is sample size of validation data. So that's the basic idea. So it's actually quite simple. So you define your loss function, and typically there would be some natural loss function, and if you're, for instance, using regression, just use linear regression. The natural one would be the squared loss, and in binary classification it's typically the 0, 1 loss. But there are other losses, and the most popular loss actually that exists is the log loss that leads us back to the likelihood. But if you want to know more details, then look up the lecture notes from last term, or from statistical methods. So that's the idea. So the question is now, what do we do if we don't have validation data? So that sounds nice, but actually usually we don't have validation dataset because, as I said above, it's a luxury. So what to do if we do not have validation data? So the trick, what we're doing is basically a little bit like a Münchhausen trick. So we're using a method or an algorithm called cross-validation to turn some parts of the training dataset into validation data. So what comes to the rescue here is cross-validation. So how does this method work? It's actually quite easy. So I'm briefly explaining here to you the outline of k-fold cross-validation. K-fold CV, and it works as follows. So the first step, divide your training data into k folds. So a fold is just a randomly selected subset of your samples. So each fold has approximately same number of samples, and also the composition should be roughly proportional to the whole dataset. So should resemble overall data. So this means, let's say we have 3 classes, then we would like to have in each fold the kind of same proportion of these 3 classes than in the overall. So this is kind of the tricky part. So we divide your training data into k folds. So the second step is use each fold as validation data, and the remaining folds as training data. So that means we have, in the end, we get k trained predictors the predictor functions and k estimates of prediction error, and the final result is the average prediction error plus standard deviation. So we get an estimate of the error plus an error of the estimated error. Because we have k estimates, so we can compute the mean and of course the error of the mean. So that's the method of cross-validation, and there's a lot of theory also behind this, but that's not a subject of our class. So what we will do, we will use this method in the worksheets, in 3 of our worksheets in practice, to estimate the prediction error of various models and also to choose among those models. So we will select either one model or sets of models with low estimated prediction error. So with low estimation of prediction error. So you'll see how this works in practice. So last one question that comes, of course, to the mind: how to choose K. So in practice, K is typically chosen to be 5 or 10, but that's just some numbers, so we need to just be aware what we want to do. So we would like to have a balance of the following. Balance. So we would like, and these are kind of things that are playing against each other, so we would like to have large folds, which means small k, so that the prediction error can be well estimated. So we want basically large validation data sets. So on the other hand, we would like to have small folds, that means large k, so that training of the predictors is not compromised by lack of data. So we would like to use most the data for training. So choosing k equal to 5 means that always 80% of the data is used for training, and 10 would mean that always 90% of the data is used for training. So 90%, 80% used for training. And of course, every single sample in cross-validation is used both for training and for validation, but not at the same time. That's the whole point. Okay, so but how this works in practice, you'll see in the worksheets. So thanks for watching, and see you soon in the next video. Bye bye.